Hello everyone. Let's continue our discussion on setup timing analysis, and let me bring upon over here our original slide. Okay, so this was the condition that we have arrived to. We said that the combinational delay should be less than the clock period minus the setup time. So this was after bringing one of the practical scenario onto the equation. Okay, so let's try to move on and bring in more practical scenarios. The next one that we'll be talking about is about something called as jitter. So what happens is this clock is been created by a PLL, by a phase lock loops, or there is some clock source that is present over here. So that clock source is expected to send the clock signals at exactly 0t, 2t, and all those time periods. Okay, but the clock circuitry that is being built over here, or the phase locked loops, basically any clock source which is present over here, which is sitting over here, that's again based on, or that's again made on some real chip, on some real circuitry. It has got some wires, it has got some variations, it has got some positive and negative variations. So that clock source might or might not be able to generate a clock period which provides a clock edge exactly at 0 nanosecond, or which provides a clock edge exactly at t nanosecond. So that clock source might have got its own inbuilt variation, and due to that it might provide a clock edge which can come exactly at 0, or somewhere before 0, or somewhere after 0. And similarly the clock edge at t nanosecond, the second clock edge that the clock source sends to the circuitry, that can arrive at t nanosecond, or before t nanosecond, or somewhere after t nanosecond. The variation will be very minimal, but there is an amount of variation, and that variation is basically because of the inbuilt variation of the clock source generation. Okay, so that's basically called as a jitter, and there is a temporary variation of the clock, and as a result of that there is a temporary variation of the clock period. For example, if let's say there was some variation in the clock source, or the PLL that is supplying the clock. The PLL is basically a circuitry that generates the clock period, that generates the required clock period. Okay, and because of its inherent variations inside the PLL, it sends a clock edge at so let's say at this edge, not at 0 but at this edge, to the launch flop, and the next edge that the PLL sends to the capture flop is at this particular edge and not at 1 nanosecond. So initially the period was from 0 to t, and now it has shrinked from this point to this point, and which is definitely less than 1 nanosecond. So this temporary variation of, and this is a very less variation, but this still accounts for failure of the for failure of the circuits. And the reason is because the combinational delay that we have analyzed this circuit for was kept as less than t minus s, but now the combinational delay requirement becomes even more stringent because of this kind of variations, and those variations are captured on a term called as jitter. Jitter is referred to as temporary variation of the clock period. Okay, and as a result of that, this has to be modeled somewhere in this particular equation only, because there is no other way to control the non-idealities of the PLL. So to capture or to model the non-idealities of the PLL, let's try to do it over here itself, and let's try to bring this particular equation to a more real scenario. So initially we had like combinational delay should be less than the clock period minus the setup time. Now let's try to bring out one more parameter to model the jitter, or to model this particular temporary variation of the clock, and let's club this variation and this variation onto a single parameter called as uncertainty, and let's bring it over here. Okay, so now your clock period, your combinational delay, which was supposed to be less than t minus s, It was supposed to be less than t minus s, and now it will be less than t minus s minus su. Su is the setup uncertainty because we are doing a setup timing analysis. Things are different for the whole timing analysis because in that case there is only a single edge that comes at the launch and the capture flop. So this can be a more relaxed. We'll come to that in some time from now. But in the setup timing analysis, since the different edges goes to the launch and capture flop, and as a result of that, there will be different jitter values for the launch flop and the capture flop clock edges, and as a result of that the window looks a bit bigger over here, and as a result of that now the combinational delay should be less than t minus s minus setup time minus setup uncertainty. Okay, so if you try to bring into some real numbers over here, so if we try to bring in real numbers over here, so the clock period of 1 nanosecond and setup time of 10 picosecond and uncertainty of 90 picosecond, your combinational delay requirement becomes t minus s minus su, which is 1 nanosecond minus 10 picosecond minus 90 picosecond, which comes to roughly around 0.9 nanosecond. So this is your new combinational delay requirement. Okay, so this is one of the next practical scenarios that we brought into the picture. Now let's move on and bring into some more real and practical scenarios. The next is the real clocks. So let's now try to build the clock tree and do a timing analysis with real clocks. So with real clocks, the circuitry looks a bit different. So initially if the circuit looked something like this and the clock tree was ideal, now the clock tree will look something like this. We'll have buffers, the clock edge will now reach this launch flop and the capture flop through a set of buffers and wires, and these are real buffers and wires. Okay, so if the initial equation looked something like this, now your equation, the combinational delay requirement, since we are looking into real clocks, this particular combinational delay or this particular clock delay also has to be taken into consideration. Okay, so now what happens is this particular clock edge which is at 0, for example the clock at 0th clock edge, this particular clock edge was supposed to reach the launch flop clock endpoint at 0 nanosecond. But now because of these buffers in the place, this clock edge will not reach at 0 nanosecond, but it will reach at 0 plus 1 plus 2 buffer delay. Okay, so now your conventional delay initially was theta, and the requirement was theta should be less than t. So let's try to modify this one by one. So let's try to bring up this one first. Your clock network delay, your clock edge at the 0th clock edge, which was supposed to reach at 0th time period at launch flop, it will now reach at 1 plus 2. So your theta is your conventional delay and 1 plus 2 is the clock network delay, is the launch flop clock network delay. Okay, and similarly the clock period, the clock edge which was supposed to arrive capture flop clock endpoint at t nanosecond, it will not arrive at t, but it will arrive at 1 plus 3 plus 4 plus 4 buffer delay. Okay, so it's t plus 1 plus 3 plus 4. The clock will send the clock, or the PLL, or the clock generation, the clock source will send the clock edge at 0 nanosecond over here, but it will reach the launch flop and the capture flop after this buffer delays only. This is the best way to interpret this. Okay, so let's call this 1 plus 2, which is present over here, let's call it as delta 1. Okay, and the delta 1 is nothing but your launch flop clock network delay, because this is the delta 1 is the time required for the clock to reach from the clock endpoint to the launch flop clock pin, and this let's call 1 plus 3 plus 4 as delta 2, and delta 2 is the time required for the clock edge to reach from this point to the capture flop clock endpoint. So what we'll do is, since I'm running a bit late out of time, we'll look into a more pictorial representation of delta 1 and delta 2 using this particular timing graphs. So let's try to bring the timing graphs and let's visualize the delta 1 and delta 2 in the next video. Thank you.